I have this curve here, y is equal to the square root of x, and we're interested in x from 0 to 4. And what I want to do with this curve is send it on a ride. I want to rotate it around the x-axis. So we're going to spin this guy around, and we're going to have something like this. Something like this. And then we can box it off a little bit, and then I'll even give us a little slice out of it. So it's going to look something like this. And to me, I would just describe this as a cup-looking thing. And what we've seen earlier is we computed the volume of this. We computed the volume of this. We were working with volumes of revolution. But here, I don't want to compute the volume. Instead, I want to figure out what the surface area of this cup-looking thing is. So we want to find the surface area now. Surface area. Surface area. Okay, and how do we do that? And maybe you want to pause the video and try to mess around with this a little bit. And I'll give you a hint. It has something to do with what we learned about arc length in the last couple videos. All right. Assuming that you've played around with it a little bit, maybe you have, maybe you haven't, what you're going to see is the visualization of this is going to look awfully similar to the disk method when we are computing volumes. But when we compare those two things, we need to remember the disk method finds a volume. And what we talk about now with surface area, well, it finds surface area. So they're two different things. They're calculating two different things, and we need to remember that. So ultimately, what we want to do, similar to when we calculated volumes, we're going to end up constructing a definite integral that is going to be summing up all of these little pieces of surface area. So in a textbook, you might just see D and then capital S. That's a little differential of surface area. I threw a subscript A on here, and you'll see why in a little bit. I just don't want us to get lost in some notation. So this is summing up all these little pieces of surface area. And what are these little pieces of surface area? That's what we need to figure out. And what we're going to do is pull out this slice. We're going to look at this. This is just a circle here. So it has a radius, and we'll just call that R for right now. And what we saw with the disk method in computing volumes was we found the area of this circle here. And then we ended up multiplying it by a little piece in some direction here. So a little dx or a little dy. And that gave us a little piece of volume that we ended up integrating. Here, again, we're not finding volume. So instead of finding the area of this slice here, instead of finding the area, we're actually going to calculate the circumference. So again, we're after these little pieces of surface area, and we said first we want to get the circumference of this. So this is 2 pi r. That's our circumference, okay? Circumference. All right, and once we have this circumference, again, we're after surface area. So if we come up to our graph here, once we have the circumference of this, to get some surface area, we're going to be multiplying by this little piece of arc length. So that's what this looks like on this slice. Multiply by this little piece of arc length, and then we get this right here. So this guy right here is a little piece of arc length, and multiplying these guys together is going to give us this little piece of surface area. And that's what we're after. So if you think about chopping this cup into slices here, you're just finding the surface area of these slices that you chop. And this right here is the new part, the new part of our information. Now, all we need to do is find what R and ds is in regards to this problem and throw it in an integral and calculate. So maybe pause the video and give that a try. All right, here we go. Let's find R first. So what is R? Well, we're going to stay up here with our picture. This, let me get white again. This right here, we can say is the radius of this slice. And you can see that this height here is y, but we're going to end up integrating with respect to x. So I'm going to express this, that y is equal to the square root of x. So the r value here, the radius of this slice, is going to be the square root of x. So we have r now. This is equal to 2 pi, and we said r is the square root of x. So that is the circumference of these slices. And now all we need to do is find a ds. Find this little piece of arc length. And we learned how to do that in the last video. We saw that ds is equal to the square root of dx squared plus dy squared. And we said we want to integrate with respect to x, so we're going to factor dx squared out of this radical here. So we're going to have this here, the square root of 1 plus dy over dx, all of this squared, and then dx. That's what we have. That is ds. And lastly, all we need to do to complete this is find what dy dx is. So that's the derivative of y with respect to x. We're told our curve is y is equal to the square root of x. So let's just take the derivative of that guy. Let's pull this down here. Y is equal to the square root of x. Let's find its derivative with respect to x. So dy dx is equal to, and remember, this can be rewritten as x to the 1/2 power. So taking its derivative, we have 1 over 2 times the square root of x. And that is our last piece for arc length here. So we find this to be, this right here is equal to the square root of 1 plus, and now we have this here in green, so we have 1 over 2 times the square root of x, and this is all squared. Let's keep our radical going here. I want yellow. There we go. There we go. And then we can't forget dx. So that is ds. And now we have all of our pieces. Let's throw this into an integral. Now, maybe I can complete this up here real quick. Let me copy paste this guy real fast. Here we go. Copy, paste. All right. This guy's going to go right here. And we found what these little pieces of surface area are now. This guy, little pieces of surface area. That's right here. Now, just throw this into an integral, and we'll make that a definite integral. So we'll throw some limits of integration on there too, and we'll be on our way into finding the surface area of this. So maybe let's switch colors. Go purple now, like that. And remember, this is going to be a definite integral, but maybe we could throw these limits of integration on at the end. I want to get this guy in our integral right now. So this is going to be 2 pi. I'll just leave it all in white. This will save us some time. This is 2 pi times the square root of x. And then we have times this right here, times the square root of 1 plus, and then let's square this guy. So this is going to be 1 in our numerator, and then we're going to have 4 times x in this denominator. So this is 1 plus 1 over, and then we have 4x right there. There we go, and then we still have dx. Now that we have this, we still need our limits of integration. We're looking at x from 0 to 4. There's our limits of integration. This right here is the definite integral that we need to solve. So we've gone through all of the new parts. Now we already know how to do this. So let's calculate this definite integral. And again, feel free to pause the video, get some integration practice here. All right, let's solve this guy. First thing I want to do, let's just get this definite integral 0 to 4, 2 pi times the square root of x. And I'm interested in this radical now. I want to get a like denominator of 4x. So we're going to be multiplying this by the square root of, and then common denominator 4x. So that's going to leave us a 4x plus 1 in this numerator. And then we're going to have a 4x in this denominator here. And then we'll have dx. And what I want to do now is I want to take this 4x out of our radical. So we'll have the definite integral 0 to 4, and then 2 pi times the square root of x. And then I want to take this 4x out of the radical. So we're going to have 1 over 2 times the square root of x, and then times the square root of 4x plus 1. So after all of that, you can see we got some nice simplifications to happen. This right here, square root of x is going to cancel, and the 2's are going to cancel. That is nice. So we're left with this. We're left with the definite integral, 0 to 4. And let's take pi out. So we'll have pi out front here. But then our integrand is going to be the square root of 4x plus 1. And then we're integrating this with respect to x. And now, thankfully, this just becomes a nice, easy u substitution problem. So let me get a new color going here. We'll go blue, and we're going to let u be equal to 4x plus 1. And then du is equal to 4 dx. And let's get some new limits on here too. So let's get our new limits of integration. What do we have for an upper limit? Let's see here. That's going to be 17. So our u is equal to 17 as our upper limit. And then u is equal to, what is our lower limit? That looks like just 1. There's our new limits. And now we can throw together a nice new integral. So we're going to have the definite integral now from 1 to 17. And we still have this 4 to deal with. So we're going to have pi over 4 outside of our integral. And then lastly, we're left with u to the 1/2 power du. That's what we have to compute now. Anti-differentiating u to the 1/2 power, that's going to be 2/3 times u to the 3/2 power. And then we still have this pi over 4 out here. And then we'll evaluate at 1 and 17. So here we go. This is the ending part. Let's do this. This is going to be what? Let's see here. This is going to be pi over 6, and then times, and then we're evaluating this at our upper and lower limit. So this is 17 to the 3/2 power minus 1. And this right here is our surface area. So we are done. And it's not a lovely answer. It's not a lovely answer. But what I wanted you to see, again, we were just computing a definite integral for the last little bit. What I wanted you to see was this initial part that we talked about, how we find these little pieces of surface area. And we found that is taking the circumference of these slices and multiplying it by a little piece of arc length.